So in this lecture, we're going to study Kepler-3 laws. Now, from the previous lecture, we know that Kepler's third law has a direct connection with the way the force of gravity depends on the distance between the two objects. That is the inverse squared nature of Newton's law of universal gravitation. So clearly, they're consistent with each other. But what about the first law and the second law? Now we're going to take a look at each one of these. Historically, Kepler-3 laws were discovered by Johannes Kepler before Newton discovered the law of universal gravitation. But now that we have the law of universal gravitation, can we derive Kepler-3 laws based on Newton's law of universal gravitation? The answer is definitely yes. Now we can take a look at each one of them separately, starting with the first law. The Kepler's first law is also known as the law of orbits. Basically, it tells you the shape of the orbit of a planet going around the sun, or more generally, the shape of an object revolving around the gravitational attraction center. For example, a satellite going around the Earth, the same idea. Basically, it says that if you consider an object of mass m revolving around a more massive object attracted by the gravitational force, then the shape of the orbit is that of an ellipse. Okay, is that of an ellipse with the more massive object at the center, at one of the two focal points of that ellipse. Now, as you know, a circle is a special case of an ellipse, and that's when the two focal points merge into one. And in that case, the distance between the two masses will stay the same, and that becomes the radius of that special ellipse, which is a circle. But in general, it doesn't have to be the case. You can have a very elongated circle. Very elongated ellipse. But in the case of the Earth, the orbit of the Earth around the sun is almost a circle. So it's an ellipse that is very close to a circle with an eccentricity value very close to 0. All right, so that is Kepler's first law. Now, how does one derive Kepler's first law from Newton's law of universal gravitation? Well, we're not going to do it here, but I assure you that can be easily done if you take an upper division mechanics course. It's a standard problem. You have to apply some knowledge of calculus. You can then derive from Newton's law of gravitation to Kepler's first law. We're not going to do it here, but you see it in the upper division mechanics class. What I want to talk about, though, is how it can be derived without calculus. You know, Newton invented calculus, right? And in his famous book, the Principia, he actually derived Kepler's first law, but he did not use calculus, the tool that he himself personally invented. Okay, that actually made his job a lot harder because calculus is such a powerful weapon that we can use to solve many physics problems, especially this one. If you do not use calculus, then you don't have this powerful weapon to use, and your job becomes a whole lot harder. And it's a very challenging problem to derive Kepler's first law without calculus. And we don't even attempt to do it here, nor in the upper division. And I can tell you, historically, only 3 people were on record to have derived Kepler's first law without calculus. The first one was Newton, as I explained. The second one was this guy, James Clerk Maxwell, the greatest theoretical physicist of the 19th century. You'll hear a lot of this name later in different parts of the Physics 8 series. His importance, his contribution to physics was monumental, especially in the theory of electromagnetism. You will see that in a later course. But more recently, another great physicist also derived this without calculus, and his name was Richard Felix Feynman. He actually was a long-time Caltech professor right across the street from our school. And there was a story about how he made this derivation. He didn't do that sort of, on purpose. He was asked to give a guest lecture to a Caltech class, but that was a lecture right before a test. So Feynman figured that students probably were not interested in something really serious or anything. He thought it was fun to, try to work out a derivation of Kepler's first law from Newton's law of gravitation without the use of calculus. And he didn't really realize how difficult this was until he started working on it. So he kept on working on it, spent almost the whole day working on it, and he got it. And his proof was then, given in that guest lecture, which was recorded. And years after he made this recording, somebody at Caltech dug out the tape file, the audio tape from his recording, along with lecture notes, and they turned this one lecture into the subject of an entire book called Feynman's Lost Lecture. So if you're interested in his ingenious proof of Kepler's first law from Newton's law of gravitation without calculus, you can read that book. Again, it's a very concentrated lecture because it was expanded into a whole book, and it's really a very clever way using only high school math knowledge to derive this famous law. So we're not going to do it here, and it's not easy at all, but you will learn a lot if you read that book. Okay, so that's from Richard Feynman, one of the greatest theoretical physicists of the 20th century. Now, the Kepler's second law is something I want to talk about more, and we can certainly derive that one. Okay, Kepler's second law is also known as the law of area. What does it say? It says, consider, a planet going around the sun. Now, if you're looking at a circular orbit, okay, with the sun at the center of that circle, then the planet will revolve around the sun at a given speed, at a constant speed, as uniform circular motion, right? And because the speed is uniform, then clearly, if you draw a line connecting the sun with that planet, so here is the sun, center of the sun, and here's the planet right here. You draw a line connecting them. We use a vector r to start from the sun and end at the satellite, ending at that planet. Then that planet, as the planet moves, this vector r will sweep out an area over a certain amount of time, right? The law of area says that the area swept out by this vector, starting from the sun, ending up on the planet, is equal for an equal amount of time. For example, look at the diagram here. Let's say the planet moves from position A to position B on that diagram, okay? And the area it swept out is A1. And let's say the time it takes from A to B is 1 month. And next, consider another segment where the same planet went from point B to point C. The time is also 1 month, and so on. And then Kepler's law, second law of area, simply says A1 equals A2. So the vector r sweeps out the same area over the same period of time. Now, again, if this is a circular motion with the sun at the center, so it's a special case of ellipse, that case is very simple, okay? Because the speed is the same, the radius is the same, therefore it certainly sweeps out the same area over the same period of time. But can we show this more generally when the orbit is an ellipse with the sun only at a focal point, not at the center of the ellipse? Can you show that? But it turns out that can be done as well. Okay, first of all, it's a little bit of math knowledge, which is quite simple too. Consider two vectors, A and B. So look at the right side of this page. Look at this diagram here. Vector A and vector B. The angle between them is theta. Now, if I connect the tip of vector A to the tip of vector B, so we're looking at between this point and this point, we connect them, okay? We connect these 2 points. Then we form a triangle, right? We form a triangle. What is the area of this triangle? Well, the area of the triangle would be base times height times 1/2. Okay, base is the length of the vector A, height is h, n times 1/2. Now, the height h in this diagram is equal to the length b, which is the hypotenuse of the right angle triangle on the right side, and then times sine theta, isn't it? H equals b sine theta, right? B is this magnitude here. B is this magnitude, the side of this length, the length of this side. A is the length of the base. Then isn't it true that H equals B times sine theta? And therefore, the area of the triangle A, B, C, let me call this point C, and this point A, and this point B, then I shouldn't be using the exact same symbol, but you know what I'm talking about, right? So look at this triangle here, then the area would be 1/2 A times H, which is 1/2 AB sine theta. But don't forget, AB sine theta is the magnitude of the cross product of vector A and vector B. Okay, so I can rewrite the angle, the area of this triangle, which is the basically the shaded area, as what? As 1/2 of the magnitude of the cross product between the vector A and the vector B. Okay, so that's a little bit of math knowledge which we need in our proof of Kepler's second law. So imagine this. Imagine you have a planet that starts out at position A, okay? It moves towards position B over a certain period of time. Now, in this process, the velocity keeps on changing, both the direction and the magnitude in general. The magnitude doesn't have to be a constant, all right? But as it moves from point A to a neighboring point, okay, right here, we can call it A prime, okay? And A and A prime very close to each other, then the position vector went from this blue one to this purple one, right? Blue one to the purple one. And what is the area it sweeps out during that time? Well, it will be this shaded area, right? And how do I write that down? Well, I can call it dA, okay? What is dA equal to? dA is equal to 1/2 times the magnitude of the cross product of the two vectors R and what? R and this little vector, don't you think, right? This little vector. This little vector is V dt, assuming the time it takes to go from A to A prime is dt, right? Then this vector is V times dt, isn't it? Okay. And if I move that dt down to the other side, then I get dA over dt equals what? Equals 1/2 the magnitude of R cross V. Okay. Now, the magnitude of R cross V, that looks quite familiar. As a matter of fact, if I multiply both sides by the mass m of the planet, m here, and m here, m being a constant, do you recognize what is in this absolute sign? Do you recognize this? What is this? I'm sorry. There's an m here. Put it back down here. Do you recognize what this is? M R cross V. Isn't this the angular momentum of the planet measured at the center of the sun? Right? So I can rewrite this as the magnitude of L over 2. Okay? So basically, this is telling me that dA over dt equals to the magnitude of L over 2m. But the magnitude of L is constant. Why? Because that's from the principle of the conservation of angular momentum. The only force exerted on the planet is from the sun. And what is the torque provided by that force measured from the center of the sun? That would be R cross F. R points this way from the sun to the planet, let's say the Earth, okay? But that's R, right? But the force is backwards. It's from the planet back to the sun. That's the force F. Clearly, R and F are anti-parallel to each other, so therefore R cross F equals 0. Okay, so the torque is R cross F, and that's 0 because R and F, the angle between them is 180 degrees. That's 0. So therefore, L is a constant, okay? So L is conserved. With conservation of angular momentum, of course, the magnitude of L is also a constant, and so dA over dt equals a constant. This is to say the rate at which this arm from the center of the sun to the center of the planet, this arm sweeps out an area. That rate, dA over dt, is a constant. No wonder it sweeps out the same amount of area over the same period of time. Okay, this is essentially Kepler's second law. So the nature of Kepler's second law really is the conservation of angular momentum. Right? So we have a theoretical understanding of Kepler's second law. Now, it does mean that if you look at a very elongated ellipse, okay, unlike the case of the Earth's orbit around the sun, look at very elongated orbital, something like this, if I draw it. So a very squashed ellipse, if you will, with the sun very at one focal point, the sun is somewhere here, okay? I mean, the other focal point is pretty far from it, somewhere over there. So this is the sun, and here's the planet, okay? You have this planet. Now we draw a line connecting them. That's the area. That's how and this is the arm which you sweep out a certain area. So it sweeps out a certain area between initial and final point, say between here and there. It sweeps out this area, which I highlight. Okay, let's say it went from here to there over a period of 1 month. Okay, now let's consider a different moment, a different period of time when it went from this location to that location. Okay, and it sweeps out the same R, sweeps out an area between this line and that line. So we're looking at a much longer triangular region. But guess what? If it takes the same amount of time to go from this point, to go from this point to this point, and then from this point to this point, let's say it's also, this is 1 month, that's also 1 month, then these two shaded areas must be equal to each other, right? So this fat triangle should have the same area as this very long and skinny triangle. But how is that possible? They have very different height. The only way to make them equal in area is when the base here is much shorter than the base there. You know what that means? It means the same planet covers a much longer distance when it's closer to the sun and covers a much shorter distance over the same period of time when it's much further away from the sun. There's only one possibility, and that is it must decrease its speed significantly as it moves away from the sun. Okay, so as a planet gets close to the sun, it speeds up. As it moves away from the sun, it slows down. That is a direct consequence of Kepler's second law, or the conservation of angular momentum. So keep that in mind. That will be useful in our explanation of this very famous special case, the so-called Halley's Comet. You know what a comet is, right? Halley's Comet is probably the most famous one of all the comets. It was discovered by the English astronomer Halley, who was a contemporary of Newton. In fact, he was a friend of Newton, and they communicated with each other. In fact, the discovery of Halley's Comet was also an inspiration to Newton's theory of universal gravitation. So here's a picture of the Halley's Comet. The reason why it's so famous is because Halley's Comet has a period of about 75 years, which means we see it once every 75 years. Okay, so here's the orbital. This is what the orbital looks like for Halley's Comet. The orbital, it looks like this. Okay, and it's a very elongated ellipse. It's a very squashed ellipse, long and skinny on this side. Okay, skinny on this side, but very long on that side. All right, so that's what it looks like. Now, how come we only see it once every 75 years? Well, so 75 years is the time it takes for the thing to complete one elliptical orbital motion around the sun. How come we only see it very briefly once every 75 years? because it spends very little time near the sun, and that is where it gets close to the Earth as well. So the Earth is somewhere here, okay? The Earth is somewhere here. And when it gets very close to the sun, then two things happen. One is the sun will illuminate the Halley's Comet, producing a tail that we can see. And secondly, this is also when it gets pretty close to the Earth. That's why we can see it, okay? Now, the reason why we see it so briefly is because when it gets close to the sun, it speeds up, okay? And therefore, it travels very fast, spend very little time in this part of the orbit. That's why we can only see it briefly. And then it spends a long time going over this vast part of its orbit, such a long distance, and travels so slowly, therefore it spends most of the time, most of the 75 years, very far away from the Earth. We cannot see it. Okay, so that's the deal. Now, 75 years is pretty close to the average human lifespan. That's interesting. That means most of us will see and will only see Halley's Comet once in our lifetime. Last time it appeared was the year 1986. Okay, the next time it will show up again is the year 2061. So here is a picture. Here is a depiction of where Halley's Comet is on a yearly basis. See 1986. See that 1986 here? That was the last time it was here. Most of you were not born at the time. And then it kept on flying. It flew away. So 1987 is already here. It went pretty fast. See that? For 1 year, when it's near the Earth, it actually near the sun. The sun is right here. Okay. So when it's near the Earth and the sun, is actually travels pretty fast. Okay, 1 year already went this far. 1988 is this 1980, 89, 90, and then you guess what? Each dot represents the new position after 1 year, and you see it slows down. See that? It slows down. The distance gets shorter and shorter. It's because when it goes very, very far from the sun, due to the Kepler's third law or the conservation angular momentum, it slows down a lot. So between say 2010 and 2011, it only moved this far, a lot less than that distance. See that? So right now, Halley's Comet is very far from the Earth. It's somewhere here. We're in 2021, somewhere here. Okay, it's actually pretty close to the extreme point of the orbit, which will happen in the year 2024. Okay, so I would actually say right now it should be somewhere here, actually, somewhere here. We are very close to the outer edge of the Halley's Comet orbit. And then in the year 2040, we'll be here, 2050 will be here. And then on its way towards the sun and the Earth, it accelerates, it goes a lot faster. Okay, so year 2060, it's here. And after 1 year only, it reaches this point where it's close enough for us to see. So expect to see it in the year 2061. The entire shape of the orbit can be calculated from Kepler's first law, and but the second law illustrates qualitatively why we only see it once every 75 years. Okay, so that's a famous example of Kepler's laws at work. Now, the Kepler's third law, of course, is something we're already familiar with. We actually use that to deduce the dependency of universal gravitational force on the separation between the two masses in question. And it basically says that T to the power 2 equals a constant times tau to the power 3. And that constant for all the planets revolving around the same center, which is the sun, is the same. In fact, this constant equals to what? It equals to 4 pi squared over gm. Okay, we saw that from the last lecture. Okay, now, if you plot t versus r, you're just gonna get a curve, and you cannot see just by glancing at the curve what it looks like. Is it a power function or is it something else? We don't know for sure. Okay. However, if you suspect that there is a power dependency between t and r, that is, t is a certain power of r. If you suspect that, then you can check whether that's the case or not by taking the logarithm of both sides. Let's say we take natural log of both sides. Okay, now we know this mass formula, log x to the power n equals n times log x, right? And apply the same formula to this case, then I have log of t squared equals to log of this whole thing, okay? 4 pi squared over gm, and then r to the power 3. And then I'm just going to apply this formula right here, okay? And then the left-hand side becomes 2 natural log of t equals, okay, so you here have natural log of a constant times r to the power 3. That is the same as, because we have natural log of x times y equals natural log of x plus the natural log of y. We know that, right? So you can break this down into two terms, x being equal to that constant, y is equal to r to the power 3. So it's natural log of x plus the natural log of y. The natural log of y in this case is natural log of r to the power 3, which is 3 natural log of r. And then don't forget, you have this 4 pi squared over gm. That's just a constant. Okay, this whole thing is just a constant. So now, if you were to plot natural log of t versus the natural log of r, you will get a straight line, don't you think? Okay, and that's what people actually did with the planets in the solar system. The y-axis is the natural log, or whatever log of the period. So it's natural log of it's log of t. Okay, so that is the y-axis in this plot. And x-axis is the logarithm of r, or more precisely, the semi-major axis. I mean, if it's an orbital, spherical, circular orbit, it's just radius. But if it's an elliptical orbit, what r we're talking about? It's a semi-major axis right here between this point and that point. The length is called a semi-major axis. Okay, so that is whatever this r means in Kepler's third law. All right, so they plotted log of t versus log of r. You should expect a slope of what? A slope of 3/2, don't you think? Okay, because that is saying that natural log of t, or whatever log of t, equals to what? Natural log of r plus this constant, which I don't even care. But what's important is slope in front of it is 3/2. It's 3/2. And indeed, that is true when you do a plot of all these planets going around the same center, which is the sun. Mercury, Venus, Earth, Mars, and Jupiter, and so on. They don't have the same mass, they don't have the same radius of orbit, they don't have the same period, which is the length of a year on that planet. But if you plot log of t versus the log of r, they will align into a beautiful straight line with a slope which is equal to 3/2. You can easily check whether that is true or not. The slope is 3/2. So that's a beautiful realization of Kepler's third law based on real life data. So Kepler first discovered it, and then now we can prove it using the Newton's law of universal gravitation. It really works. Now, you can see also, it's not just planets going around the sun. You look at all the satellites going around the Earth, whether it's the moon, the only natural satellite of the Earth, or any artificial satellite, okay, going around the sun, going around the Earth, they also satisfy Kepler's third law. The only difference is that here, this mass, we should be using what? The mass of the Earth, because we're talking about all these satellites revolving around the same center. This time, the center is not the sun, but rather the Earth. And we can see some real world examples of that as well. So that's Kepler 3 laws. You can certainly see they are really important in our understanding of how the planets go around the sun, and they can all be derived from Newton's law of universal gravitation.